Sure, it doesn't bother the deers anymore at Aberdeen. Okay, you ready?
Yep.
Okay, today we talked a little bit about cutting and plasma cutting, and I guess I could show you some pictures of plasma. Actually, I can pass these around too. These are caps to plasma torches. So you have the copper in here, and you have a ceramic layer. You actually strike an arc inside here and generate high pressure gas shooting out the orifice so far as that goes. So here's two different size plasma tips. Those are replaceable tips. We talked about oxy-fuel cutting last time. The speed can be decreased by 50% due to the high carbon in the steel, which generates carbon monoxide or nitrogen in the oxygen, and both of those create a boundary layer, whereas ordinarily the oxygen would just be consumed, there'd be no boundary layer, and you'd have excellent heat transfer, get nearly 100% of heat transferred to the surface to cut, rather than 2% that you would get from an oxyacetylene flame, where you have a big boundary layer with lots of leftover carbon monoxide and water vapor and stuff. And we also talked about plasma arc cutting being an arc jet burner, and you can kind of see the one half of the cavity where the plasma jet comes shooting out of that hole.
For the two different sizes, is the result just a different size flame? Or?
Well, you get a different length flame, and we're going to talk a little bit later today about transferred arc and non-transferred arc and how you get more heat with transferred arc where you carry current across there. But you typically can plasma cut up to maybe, I guess the largest I've ever heard of is somewhere 2 to 4 inches thick. You can get these little cheap little things I mentioned last time. They cost $1,000 or $1,500, and you can cut sheet metal up to 1/8 of an inch thick, just with compressed air and the electrical power source. A bigger plasma arc cutter has an open circuit voltage of 400 volts, so you have to be a little careful you don't electrocute people. Okay, and they're fairly safe because you're pretty much you have to design it for idiots. Okay. But 400 volts, I mean, when you're getting up to cutting through 1 inch or 2 inch thick material, you have to have 400 volts, and so the bigger one is just more gas, larger jet, more powerful jet to cut through different material. Because you're just blowing the metal away. You're just melting it very rapidly and blowing it away. So this is out of the Welding handbook, and I'll just put this one up, let's see. But there's the power supply for all of this. There's your DC power source. Here's your electrode, which could be hafnium in the little sheet metal ones, which forms hafnium oxide. You can use compressed air through here, or in the heavier ones, you use argon or nitrogen. And you can use a tungsten electrode. You have the copper, and what I just passed around is this nozzle, which is a replaceable nozzle. You strike the arc and it comes shooting out here at the workpiece. Now the question is, does current also go to the workpiece, or does it just go from the electrode to here? You have a much more complex circuit if you actually have what we call a transferred arc, which transfers more of the current to the workpiece. And that can give you a much higher heat transfer, which we'll talk about. But that's the basic type of thing. The whole torch design, you just have this little screw-on. Actually, you have the little screw-on tip right in here. This is a handheld one, but just a bunch of copper so far as that goes. So that's plasma arc cutting. Any other questions on plasma arc cutting before we get into the physics of arcs?
What kind of DC voltage is required for that?
About 400 volts, open circuit. Now the actual, if you're an electrical engineer, you know anything about power supplies, you have a voltage current characteristic for a power supply, and typically it's droopy like that. And this is the open circuit voltage when you have zero current, and that would be about 400 volts. When you're actually running at 100 amps, you may be at 100 volts. So your actual cutting voltage is 100, but your open circuit voltage, just because of the physics of the power supply, is about 400. That's why you have to be careful. And plasma arc welders tend to be something that's starting out at 100 volts and going down to 30 volts. So it's something similar, but 100 volts will kill you too. Okay, so plasma arc welders, which is a fairly similar torch, You also have to be careful because you have big open circuit voltages. But you can have open circuit voltages of 80 volts just with a stick electrode welding machine. So you have to be careful with that too. People have electrocuted themselves with stick electrode welders.
How much does the voltage matter? The voltage is what's making the spark, which is igniting.
We're going to talk
the
about that
flame.
today. Voltage turns out not to be important. It's current. It's the electrons that carry the heat. We're done. That's what today's lecture is about.
What did you say?
Can you hold for a little bit? Yeah.
What did you say was the coating?
Pardon?
What did you say was made of the coating?
The coating, the ceramic there? Oh.
Actually, ceramic.
It's a ceramic.
Okay.
It's probably a high aluminum oxide. It's nothing spectacular. Those tips probably cost 15 or 20 bucks, and you throw them away every half hour or hour of cutting time. Okay. So I mean, if you're just cutting intermittently, it might last for a week. If you're in a production operation on a cutting table where you're cutting, you might have to replace them every half hour or every hour. Okay, but it's a consumable, and it's no special ceramic. It's just a reasonably high temperature ceramic. Okay.
How you weld the ceramic with the copper?
It's just glued on. Actually, I didn't bring it. I actually have one that's broken, and you can see it's just glued on. And I'm sure it's a reasonable temperature glue, but the copper is water cooled. So the stuff you're gluing it to, I mean, the tip can get hot. That's why you use ceramic. But right next to it, the copper is water cooled, and so the copper doesn't get that hot.
Any way to make them last longer than that? Because I would think having to stop your line to replace tips every 15, 20 minutes is...
Well, that's better than 5 minutes when they first started dealing with this process, okay? But I mean, they have improved it up to about an hour, and they continue to try to improve it. But when you've got flames of 20,000 degrees shooting out through that hole,
Yeah.
it tends to erode away, and there's not that much you can do about it, okay? And they've done a lot to improve it, and they've probably improved it by a factor of 10 or 20 since they first started making these things. By the way, the guy who invented this plasma arc cutting process up here at, he was working for a guy who's an MIT grad. Can't remember his name right now. Bob. Anyway, he's an MIT mechanical engineering grad. And he's sort of an inventor. He's invented all kinds of things. But he was a professor at Dartmouth, and his student, Dick Couch, essentially came up with this idea for plasma cutting, and Dick Couch is now a billionaire, okay, because of plasma cutting. And the two big plasma cutting companies in the world are Thermodynamics and I can't remember. They're both located in Hanover, New Hampshire, because of Dartmouth College, and Dick Couch was doing his doctoral thesis under Bob, I can't remember Bob's last name. But anyway, at the time, when he invented plasma arc cutting, and I don't know the full history of how the company split up and stuff, but they're now competitors. But they own probably 90% of the world's plasma arc cutting business. Okay, and it is the big reason that it's increased in use in the last 15 years is because of environmental reasons. Okay, although it does have certain technological advantages, it can cut the stainless steel. It can cut more than just carbon steel. It can cut aluminum. It can cut virtually anything that can be melted, which is anything. Okay. Okay. Other questions? So let's talk now about flames or arcs. I'm sorry, arcs. And an arc is just an electrically augmented flame. Okay. We know we have this boundary layer problem that limits the heat transfer from a to the surface from a hot gas jet. And we learned about that in flames, and that's one of the reasons I started out in flames, to just get to the basics of how a flame heat transfers heat. Well, so we have in an arc, we have an electrode, and we have a base plate, and we make one of them negative and one of them positive. This, with electrode negative, is what we call straight polarity as the jargon. The official name is electrode negative, which is sort of self-explanatory. It can also be electrode positive. If I'm dealing with a process where this is a tungsten electrode, this will typically be what we call straight polarity. If I'm dealing with a process which is a stick electrode, you know, stick electrodes, the little mineral-coated rods or cellulose-coated rods. This is typically reverse polarity, so the electrode becomes positive, and that will hopefully today or tomorrow become obvious why we change the polarity for the different types of welding processes. You also can run this whole thing as AC. But nonetheless, Sir Humphrey Davy, back somewhere around 1805, was working with Leyden jars, which were just basically capacitors, and he discovered the electric arc. And the reason it's called an electric, he called it an arc, is because he had two carbon electrodes, and he had them horizontal, and the arc formed an arch because the hot gases are buoyant and they vaporize up. But he struck an electric arc between two carbon electrodes. The hot gases formed this little arch, and he called it an arc. Okay, an electric arc. No one did anything with the electric arc commercially until the 1880s, and I've already told you the reason why it waited until the 1880s. Why? If I remember, guy's name Edison and Westinghouse. There was never a source of high current electricity readily available. You had to have this big bank of Leyden jars, capacitors. Basically, Leyden jars are just electrolytes with metal plates in them. They were batteries, basically. And there's actually a picture. Some of the first arc welding patent was supposedly Bernardos, and was a Russian, but I never could figure out the Russian-French stuff in the 19th century. But there's a picture, a woodcut engraving, showing this room with a big bank of Leyden jars, and people were doing electric arc welding. And Bernardos, who was this Frenchman, but he took his patent out in Russia or something, basically patented the arc welding process in 1870 something or whatever. But no one ever used it very much because the problem was they were using bare electrodes. It's just a steel rod, okay, like this, and they would melt it off, and it melted just fine. By the way, Sir Humphrey Davy, within 1 or 2 years of discovering the electric arc, used it to try to weld, and he did do some welding in before 1810, but it wasn't anything commercial. But when they tried to weld on steel, which was the most common material, the problem was that you ended up with Swiss cheese for your weld. And actually the problem gets back to nitrogen in the air. They weren't using any shielding gas, and they essentially, with no shielding gas, you get nitrogen from the air dissolve in the steel, and it dissolves about 10 or 20 times as much in liquid iron as it does in solid iron. So as the steel solidifies, the nitrogen dissolved from the air while the steel is molten comes out as bubbles, just like your Sprite. You know, pop the top on the Sprite and the CO2 bubbles start coming out. Okay, well, as it solidifies, the nitrogen bubbles would come out, and you'd end up with Swiss cheese for a weld, full of pores. Okay, so it wasn't the strongest thing, and that people weren't as skilled, and the current sources weren't as stable. But people used it, but not for critical applications. And I mentioned to you the first big critical application for welding was the big inch pipeline in the 1930s, a 30-inch diameter pipe that carried natural gas from Louisiana to New Jersey. Okay, critical because you don't like to have one of those things let go. In fact, I was involved in the investigation of the fracture of one in Edison, New Jersey, a 42-inch pipeline, 900 psi of natural gas, let go one night, and they had flames 600 feet in the air. Okay, and the radiant heat melted the roof of the apartment buildings next door. Okay, nobody got hurt. The interesting thing in that story, the reason these pipelines, because they are critical, they do all kinds of corrosion protection. And this January, when we do the corrosion thing, we can talk about corrosion protection. But they actually fly an airplane over the transmission line once a week to make sure no one's digging. I mean, you've seen the signs, don't dig here, there's electrical cable underneath, or sometimes it'll say gas pipeline in the area. It's not a good idea to go digging where you have pipelines or hidden things in the ground, whether it be electrical or gas or oil, because you can have things go boom in the night. Well, so once a week they would fly over this area, and they never saw any construction going on until they had this explosion in the early 90s, and they traced it back, and they had a gouge. They had a number of gouges on the pipe, and clearly a backhoe had scratched the corrosion protective mastic, basically tar on the outside of the pipe, and it was like a 5/8 inch thick pipe, and one of the gouges was like 3/8 of an inch deep, and then the rest of it had just by fatigue, variation in pressure over time had grown, and then it got big enough that you got a brittle fracture and the whole thing opened up. And you had this 600-foot flame, which disturbed a number of the neighbors. Now, you don't usually have that happen. There's actually about a half a dozen of those that happen somewhere in the United States each year, but usually it's in the middle of some farmer's field. And you blow up a few cows and pay the farmer for the cows. And it doesn't usually happen in a residential area. Well, this part of New Jersey was not residential when they put this pipeline through. This got this right away back in the 1930s. This was a newer pipeline, but nonetheless. And they have different requirements if you're going through an urban area, a suburban area, or a rural area in terms of the safety factors on the pipelines and all this other stuff. Well, the story I want to tell is the break occurred in an asphalt plant, you know, where they basically would recycle asphalt when they're resurfacing the streets and stuff. In this asphalt plant, they had a pond, I guess, to use water somewhere in the recycling process. And the pond would sometimes be moved from place to place, and the pipeline went, you know, like 20 feet underground or 10 feet underground or something underneath all this. The reason they could never see the construction was because the digging, and they had earth moving equipment there, backhoes and stuff in the asphalt plant, was probably being done in the pond, the shallow pond. So if they're not actually actively digging, when the airplane goes by, you're not going to see it. And of course, the asphalt company said, "Oh no, we haven't had anyone dig in this area for over 20 years, not since this occurred in like 1992. They traced, I can't remember. They hadn't had anybody dig in the area since 1983 or something like that. The only thing is, when they blew the hole out of the ground and they were cleaning up, they found an entire Ford Bronco, 1988, buried underground. Okay? So the idea that no one had been digging there since 1983 probably wasn't true. Okay? Now the question was whether the mafia owned this asphalt plant. People always ask, was Jimmy Hoffa's body in there? You know, but nonetheless, it was because of the gouge on the pipeline. And that type of thing occurs fairly often. I've got a situation in upper New York State. Some guys broke into a site where they stored equipment, and they decided to play around with the backhoe one night, okay, just vandals basically. And they broke into this locked storage area, and they went digging in the ground, and it had a gasoline pipeline, and they punctured the gasoline pipeline, and so there's a major environmental spill, and now people are fighting over who's responsible. The company that owns the backhoe says, "We had it locked up, we're not responsible for vandals coming in and destroying your pipeline." The pipeline company says, "Well, you broke our pipeline." And they said, "No, we didn't, the vandals did, go sue the vandals." Well, no one knows who the vandals are, so anyway. But like I say, these types of, there's a reason why you should call dig safe, okay? And not go digging holes without knowing what's in the ground. But in any case, getting back to arc welding and safety and whatnot, that was a nice digression. It didn't have a lot to do with arcs, but an electric arc, there are lots of different types of electric arcs, and if you plot the voltage this way versus the Z direction, you'll find that you have a big voltage drop over like a half a millimeter or so, and that might be on the order of 4 or 5 volts, and that voltage is called the cathode fall voltage because the negative electrode is the cathode. Then down here at the anode, you have another steep voltage gradient, and that's called the anode fall, and that might be 2 to 4 volts. And in between, you have what's called the plasma column. The plasma column typically has a voltage gradient, electric field. Remember, the derivative of voltage with respect to distance is the electric field. It's 10 volts per centimeter. So if I have a centimeter long electric arc, I might have 18 volts. 10 volts for the centimeter long arc in the plasma column, and 4 volts up here, 4 volts down here for the fall voltages. Okay? And the reason you have the fall voltages is because the plasma is not as hot when it's next to these solid electrodes. The plasma itself may be at 10,000 degrees Kelvin, and right next to the electrodes, we may only be at 3,000 degrees. And there's not enough free electrons to carry the current, and so it takes a big voltage to punch the electrons through that boundary layer of cold gas at the electrodes. When I say cold, 3,000 degrees is not that cold, but for a plasma, it's very cold. Okay, you don't generate a lot of electrons in a 3,000 degree gas. Okay, so that's the electric arc, and 99% of the current is carried by the electrons in a high pressure arc. Inside this arc, I have electrons and ions. Okay, I had a neutral gas, and it splits it up into electrons and ions. But the electrons are much more mobile because they have 1/2000th the weight, the mass of a proton. And the ions have many protons and many neutrons, so the electrons have, you know, many times less mass, and so they are accelerated more rapidly by this electric field. Any charged particle will be accelerated in an electric field. Okay? Remember your electricity, the force on a charged particle is proportional to the field, and F is equal to ma. I mean, we're getting back to some pretty basic stuff here, but if the mass of the electron is much less, it will be accelerated under the electric field force much more quickly, and therefore the electrons have about 100 times more mobility than the ions in the plasma, and 99% of the current is not due to the ions, but it's due to the electrons. The ion current, which goes in the opposite direction, is only about 1% of the current, and it turns out, we're going to see, it's the charged particles that carry all the heat, which is why voltage is not important. It turns out current is what's important. Yep.
Just gonna ask from the diagram on the left, is that the tip on the top and then the metal surface that you're actually welding on the bottom, or is that just inside?
Those are
of
blue. The two blue things are metal.
Well, is all of that like inside of the nozzle?
No, there's no nozzle here. There's just an open arc.
Okay.
Okay, and I got an electrode, and I got a surface. In this case, they're both black, and I just strike an arc in the air. Blinds everybody in the room. Okay. So you can put it inside a copper-cooled nozzle, in which case we don't call it gas tungsten arc welding, we call it plasma arc welding, which is like plasma arc cutting. It's just like those nozzles that you had there that I passed around. But right now I'm just talking about the simplest type of Sir Humphrey Davy arc. Although we're running it vertically, he ran it horizontally. Okay. But that's the basics of an arc. But if you go a little bit further into arcs, there are all kinds of arcs. And in fact, Carl Taylor Compton, anybody know who Carl Taylor Compton was? He was president of MIT. Okay. But before he was president of MIT, actually the Compton family came from Worcester, Massachusetts, and several of them were professors of physics at Princeton or whatever. One of them came here, was president during the Depression of MIT. But Carl Taylor Compton studied electric arcs, and he defined an electric arc as a discharge in a gas or vapor with a voltage drop, which is that voltage drop at the cathode, in the cathode region that is on the order of the lowest ionization potential of the gas or vapor in which it burns. Now, the ionization potential is how much voltage does it take to strip an electron off the atom. So if I got argon atoms, it might be 5 volts. So the cathode fall voltage would be on the order of 5 volts. And he says that's an electric arc. Okay? What he's really talking about is a high pressure arc. If you go to, and you've got a copy of this in your notes, but this is from a book, Arc Physics by Max Hoyot, who was 1968, it's kind of an old book, but he was a scientist at Westinghouse Research Labs in Pittsburgh and wrote a book on arc physics, which was clearer than most of the stuff the physicists write. There's plenty of there are plenty of plasma physicists here at MIT, most of whom would not be able to give this lecture because this has to do with welding arcs. They're interested in fusion arcs for plasma fusion. Okay, tokamaks, these $10 billion, demonstrations of fusion of deuterium and tritium and things like that. And we got a number of them over in the nuclear engineering department, and MIT has its own plasma fusion center and stuff. And those guys know a lot more about arcs, about plasmas than I do, but in fact, they asked me to write something about high pressure arcs because they don't really do anything with high pressure arcs.
You mentioned something about blinding from the arcs. What types of processes are really the ones that can blind and from a PPE standpoint?
Any plasma process. The flames, most of the flames will not sunburn your eyeballs, and that's really what happens. Okay, it's the the radiation hitting your eyeballs, and actually your eye focuses it. We draw an eye, and the typical way you draw an eye is like this. So there's your eye, and when the light comes in, your eye will focus that radiation back here on your retina. And the reason you have to protect your eyes from lasers is because the laser may not be intense enough out here to burn your skin, but when it goes through this lens, which is your eye, it doesn't take much to burn your retina. If you burn your retina bad enough, it can blind you. Now typically, you can't do that with radiation from an arc plasma, and actually if I go back to, should have a picture of it here. This old thing that you've seen so many times. And it's something I never emphasized for you on this plot. But the guy plotted down here in watts per square centimeter the temperature in degrees Kelvin of blackbody radiation. A blackbody is something that you're talking about 100% efficiency of re-radiating the light. And a 1,000 watt per square centimeter oxyacetylene flame has an arc temperature, or has a temperature equivalent. And this goes back to the Planck radiation law, if you know anything about light and stuff, of about 3,600 degrees Kelvin. Well, that's like a flash from a light bulb, okay? And that can, if you look continuously at the flash from a light bulb, that will, your eyes will be hurting at the end of the day, which is why if you're using oxyacetylene, if you're doing oxyacetylene welding, you wear some glasses, not a full face shield, but you use some basically good sunglasses, okay? And that will cut down the light intensity, and you won't burn your retina. You will start to sunburn your retina if you didn't wear sunglasses, just like on a, you know, just like skiing, okay? And you get all the radiation off from the sun. You need to have some good sunglasses. These are darker than the average sunglasses. For arc welding, you can sunburn your eyes within tens of seconds of looking at an arc. Not within a second. If you get flashed for a second, you're not going to sunburn your eyes. I remember once I was watching a demonstration. Remember these great big LNG carriers where you have these big aluminum spheres, and in some places at the equator that aluminum's like 2 feet thick. In other places it's like 3 or 4 inches thick in the major shell. But they have 5 of these great big things that carry and some of the liquid natural gas tankers. And I was at Alcoa Research watching a demonstration of welding 2-inch thick aluminum at 600 amps with an arc weld, and I was holding a face shield, okay, but I was holding it, I didn't have any gloves on. The next day I was at a welding conference in New Orleans, and I had this sunburn on my hand. I had only watched that thing for 60 seconds, 120 seconds, 1 or 2 minutes. But I was like from here to second row here, and I had gotten a sunburn, okay? I finally realized what it was. It was from that 2 minutes of watching that high reflectivity aluminum 600 amp arc had sunburned my skin in 2 minutes. Now if that had been my eyeball, I probably would have been blind in 2 minutes. That was very high intense, 600 amp arc, So it depends on the arc, but you're at 6,400 degrees or 6,500 degrees Kelvin, and it doesn't take but a few minutes. And then if you've got focusing on the eyeball, you can sunburn fairly badly. People do get arc flashes, and I've never had it, but you can get essentially a light sunburn, and they say it's like having sand in your eyes for a day or two, okay, until the edema, which is the redness, goes away. And usually there's not any long-term damage unless you really burn it, second-degree burns, yeah.
If you burn it bad, can that cause permanent blindness, or is it usually just temporary?
If you looked at an arc for 10 minutes straight, you probably would have some permanent loss of sight. And if you looked at it for 30 minutes, you'd be blind. Okay, it'll burn your eyeballs. If you get second or third degree burns on your retina, it won't repair itself. But if you just get a little redness, typically, I mean, if you do it every day, obviously probably it's not a good thing, but supposedly it feels like sand inside your eyes, okay, until it goes away. So there's that, and actually if you get here to lasers, electron beams, you're getting to blackbody radiant heat intensities of 20,000 degrees, and that could do things very quickly, which is why laser radiation can damage your eyes within a fraction of a second, okay? Because you've got such high radiant heat fluxes. Okay, other questions? Yeah. Getting back to this, you can define arcs in lots of different ways because there are lots of different types of arcs or plasmas. If you're talking about approximate voltages, and this is on a scale of 1,000 to 2,000 volts, and approximate currents going from picoamps up to 1,000 amps, this is what the voltage current characteristic looks like for arcs, okay? Actually, he calls them electrical discharges because they're not really arcs except in this region, which is what we call the high pressure arc. We have dark discharges at very low currents, and they tend to be very low pressures, not very strong plasmas, weakly ionized gases. We have glow discharges. A glow discharge is nothing more than that fluorescent light up there. And the voltage in that glow discharge is hundreds of volts. If you're familiar with these fluorescent lights, many of them have a ballast, which is a transformer, which takes the 100 volts and takes it up to 1,000 volts, okay, in order to get a glow discharge. And you can have, as you go to the transition, something we don't usually use anything commercially, we have an abnormal glow where you get high voltages, and then it drops very rapidly to an electric arc. And the electric arc can have a drooping characteristic, or it can have a increasing characteristic with current. High pressure arcs are where we do welding. And none of the guys in the physics department are interested in high pressure arcs. They were all studied in the 1920s and the 1930s. So all the interesting science from their point of view is in these other types of plasmas or fusion plasmas, and regular old arcs are just some sort of thing you use for welding or cutting or something like that. But this is called a high pressure arc. Anything above, and we've got another plot down here, anything above about 1 amp or half an atmosphere pressure is called a high pressure arc. And why do we call it a high pressure arc? Because a high pressure arc is in a state of what we call local thermodynamic equilibrium. Only at MIT would we start talking about a simple arc and start talking about different things. But this is pressure versus temperature for arcs, and this is a low pressure arc, this is a high pressure arc, and here's the transition, which was that abnormal glow region. In a high pressure arc, the temperature of the electrons, which are the negative particles, the temperature of the ions, and the temperature of the gas are all approximately equal. That's actually an approximation sign, not an equal sign. And in a high pressure arc, that is the definition of a high pressure arc, where all of these particles are approximately at the same temperature. Now, what do we mean by approximately? The temperature of that arc might be 10,000 degrees. All of them are 10,000 degrees within 100 degrees of each other. Okay? They can't be at true they can't be at true thermodynamic equilibrium, because thermodynamic equilibrium says nothing's going to change with time. And I've got positive ions, negative electrons, neutrals, just do neutral gas atoms, and I got a whole mix of these things inside some chamber, and I've got an electric field on it. Okay? And the electric field, the electrons are going to move, going to be accelerated. The ions are going to move more sluggishly. They're like molasses compared to the electrons. And the neutrals are not affected by the electric field at all. Well, if this one's accelerating, it's gaining velocity, and more velocity means more energy means more temperature. So it can't be at the same temperature as that. But what happens is if I'm in a high pressure arc where all these are relatively close together, that electron hits one of the others and gives up some of its energy to them before it can get accelerated again. And so when they're close together, they have what's a small mean free path. Okay? The distance between them is so small that the temperature difference between them, because they're banging around together, is going to be small. And so they're within 1 or 2% of the same temperature. And this is a plot of temperature. As you get to lower pressures, now you get to the point where these things are so far apart in this chamber, that electron can go zipping along, getting very high velocities, very high effective temperatures, whereas these other guys that are running around like molasses don't pick up, well, the neutrals don't pick up any energy from the field. The ions pick up some, but not as much. And so it turns out you start to get, as you get to lower and lower pressures and larger mean free paths, you get to the point where the electrons end up with much higher temperatures than the ions. And that's a fluorescent light. Yes?
What causes that increase again?
Down here?
Proton, yeah.
Down here, these guys are still close enough together, they're transferring energy between themselves. So the two are transferring energy between these two heavy masses. Over here, the distance between them is getting far enough apart that the ions are going to start accelerating in the field, whereas the gases don't. Okay? So it's the same thing, but it's just a slower process that goes to larger mean free paths.
Keep talking about, you know, some type of gas that is used in the process.
Yep.
And you said way back when, you know, they had Swiss cheese welds.
Yep.
So basically, if you're trying to stick weld and you don't have another type of gas, you're going to end up with Swiss cheese weld. Is that the deal? Or
If you have air, if you have nitrogen in steel, you're going to end up with Swiss cheese. Which is why, and I'm going to get into tomorrow, different gases we use in welding. We use argon, we use CO2. We use things to get rid of the nitrogen. And when we're doing stick welding, we actually have carbon monoxide or CO2 generated by that flux, or water vapor and hydrogen generated by cellulose in some of those electrodes, which actually the electrode creates its own gas. That flux coating creates the gas to exclude the nitrogen. Okay? If that's what your question, sounds like that was your question really was.
Yeah.
Where's the gas coming from to get rid of the nitrogen in those other processes? And when we use bare electrodes, you will get Swiss cheese, but when you flux coat them. And in fact, the story goes that there's two types of shielded metal arc electrodes in this country. One is called cellulosic electrodes, and it was developed somewhere in the United States, and I don't know that we know who developed it, but people were welding with bare electrodes in around 1900, and some guy wrapped some paper around his electrode and found the porosity went away. And what he was doing is he's burning off the cellulose, and cellulose is a hydrocarbon, and it forms carbon monoxide and water vapor in the oxygen. And as it burns, you actually, if you analyze the gas in that arc, you'll find it's about 60% hydrogen and about, I can't remember, 5 or 10% water vapor and 10% carbon monoxide and 5 or 10% carbon dioxide. But it's basically, you exclude the nitrogen by burning up cellulose, okay? And that's the origin of the E6010, 6011 electrodes. If you know electrode designation by American Welding Society, some of you do, some of you don't. Those are cellulosic electrodes. Those are high hydrogen. Don't weld HY100 with cellulosic electrodes because you get hydrogen cracking. At about the same time, and we do know, I think it's, if you go to the ESOB weld site, ESOB is a Swedish company. It was founded in Gothenburg, Sweden, and I can't. This is all for Swedish words. I can't tell you what it stands for. ESOB still exists, and in Gothenburg, Sweden, some guy around 1908 stuck in his name is on the website, and he founded ESOB. Some guy stuck his electrode in some mud, and he found it welding with a muddy electrode got rid of the porosity, got rid of the nitrogen. In this case, the mud, actually in that case the mud was also giving off water vapor and other things, but people have since learned to make mineral coated electrodes, things that have titanium dioxide or calcium silicate, different types of mineral electrodes, And those are things like E7018 electrodes, which we call low hydrogen electrodes. And that is what you weld your high strength steels with, so you don't get hydrogen cracking. Low hydrogen electrodes, and you have to keep the moisture off the electrodes. We can talk about that some later. But in any case, there are two types of electrodes, one developed in Europe, the beginning of the ESOP Corporation, mineral coated electrodes, and the other one here in the United States, cellulosic electrode. Both of them are used around the world. The cellulosic electrodes are easier to use, it doesn't take much skill. The others make a higher quality weld deposit, but it takes a little more skill to weld, and it takes more care of the electrodes. If you've worked in a shipyard, you know some of those electrodes go directly from a rod oven, and they count them out, and the welders have to bring back the stubs, same number of stubs as they were issued, okay, to the electrodes. Because if you drop one of those stubs on the floor, not only can someone step on it and fall, but more importantly, if they pick up an old stub that's been sitting around gathering moisture in the flux for the last week, and they weld one little, repair job or one little tack weld or something with that moist electrode, you can get a hydrogen crack, which can cause the whole thing to fail later. So in a pressure vessel shop, if an inspector sees an electrode stub on the floor, you lose your license. Okay? And you have in a shipyard, in a naval shipyard, they will typically issue you the electrodes from the ship stores. They will count out maybe 40 electrodes, and you have to bring back 40 stubs to get some more electrodes for the second half of the shift. Yeah.
Did you hear about what happened at, I think it was Newport News? They had some of those problems with the pipe welds.
No, I didn't hear about that.
They, I think one of the things they wanted to save time, so they give out a welder coming in, have a couple jobs, so they give different electrodes for those jobs.
Right.
But the problem was they get mixed up then, and they were welding, one type of pipe with the wrong electrode, and they had a lot of weld problems.
Okay, yeah, well, actually, I guess I did hear a few years ago about a bunch of weld problems, but I didn't know the details of it. Those electrodes have little dots on them, or they even have the number of E7018 on the side. Maybe I'll bring some tomorrow, and you'll see. They're labeled, so it's because the welders weren't trained, okay? It wasn't because the electrodes weren't identified properly. Plus, they have different colors. The fluxes come in different colors. Not necessarily because they're trying to color them, but, it's easy to identify them, okay? So that was a lack of training on the welders, or a careless on the part of the welders. You do have to weld with the right electrodes because they have different strength levels, they have different hydrogen levels, they have different electrical polarities for your power supply, okay? There's lots of different things. So yes, people, it's Murphy's Law, something can go wrong, someone will screw it up, right? Okay, so let me just finish up a little bit on this. So now you can understand a lot about lighting, and you can understand something about incandescent lights, fluorescent lights, and LEDs now. In an incandescent light, which is what Edison invented, you heat up, he started out with little carbon strips, okay, horsehair, they are carbonized, but later people got to tungsten, and you have an incandescent light, you heat everything up, and everything in there is at a similar type of temperature. You can think of it, it's not an arc, but everything's, the gases, the ions, and the electrons, it's the electrons vibrating that give off the light, okay, that's what gives off light. Electrons going through a curved path in an electric field, or vibrating, if you want to think of it as vibrating, but electrons radiate if they curve, okay? If they go in a straight line through space, no emission, but if they are forced into a curved path, the electron will give off radiation. If the radiation is the right temperature radiation, you'll see this visible light. Even if it's lower temperature, not as strong an arc or curved path, it'll be infrared radiation. If it's an even sharper curved path, it'll give off ultraviolet or X-rays even. Okay? Ever heard of the free electron laser? Okay? People are trying to vibrate electrons very rapidly and give off X-rays from electrons, turning corners, basically. But anyway, an incandescent light is just hot gases. And those hot gases are consuming most of the energy. So your incandescent light is maybe 5 or 10% efficient or less, okay? Because it's hot. You ever unscrew one when it's hot. You can burn your fingers. In a fluorescent light, they're about 2.5, 3 times more efficient in terms of energy usage because the ions are cold down here, less than 100 degrees or a couple hundred degrees. This is Kelvin. Okay, basically at room temperature. You can grab that fluorescent light while it's operating and you don't feel any heat. But the light given off is given off by the electrons, which are at 10,000 or 20,000 degrees. Those electrons are in a low pressure and lots of space in between, and they can create, they can go in curved paths. In fact, they go in a helical path by nature due to the electric fields, and they will give off light. And they're giving off light as if they're at, as if the whole thing, or certainly the body giving off the light is at a temperature of anywhere, actually in a fluorescent light, 50 to 100,000 degrees. Okay, so, but you're not heating up all the mass. All the mass down here is not hot, it's cold, and so you have a much more energy efficient system. So what happens in a light emitting diode? In a light emitting diode, you don't even have to worry about the gas. You are just heating up the electrons in a little laser in that piece of silicon. Okay? And now those electrons are giving off almost all of your energy, actually probably about 70 or 80%, I don't know exactly, is actually can be converted to light at very high effective temperatures. Okay? So LEDs are very energy efficient, as you know. If you get a LED flashlight, the batteries last forever, sort of. And you get a incandescent light, get a Coleman lantern, you know, the batteries last a long time. If you get an incandescent light, then you'll burn up your batteries fairly quickly. So now, that's my fluorescent light lecture, as I call it. So you now know how fluorescent lights work. Okay? We'll see you tomorrow.